So this is the last lecture of this coursework, and this is also an application that we have done in our group, and one is the recent one published in this year, another one is the old one. Both are given here with some purpose. So the first one is the application of Raman spectroscopy in elucidating some structural aspect of milk component, and the second one is that how Raman spectroscopy helped us to elucidate the structure of ionic liquid, a new material. So milk, all of you know, this is one of the most important food for our daily diet requirement, and almost everywhere, every country consumes milk. Every citizen usually consumes milk. And if you see that how much milk is studied by particularly this Raman spectroscopic instrumentation, then in the recent time, like 2011 onwards, there is a significant increase of publication, number of publication, in which either Raman studies, Raman spectroscopy of milk, this keyword, or Raman studies of cis and trans fatty acid, these terms are there. Means this many, like 2023, you have around 13 publication in which these two keywords can be found. Means those publications are specifically devoted for this application of Raman spectroscopy in milk studies. So our aim is or was to study the milk, and the milk is the Banaras milk, because it is well known that this Banaras milk is very famous compared to the rest of the India's milk. So we wanted to study whether there is anything unique feature available in Banaras milk, and that can be studied by the Raman spectroscopy. Because we know the Raman spectroscopy can elucidate the presence of some unique molecule or the presence of unique conformation. And as you have seen in the last lecture, that he has nicely studied this glucose, so-called glucose sugar solution with hyper Raman spectroscopy, which at the initial stage he told that it is a pessimistic studies, because hyper Raman, IR should be same for a non-symmetric group of compound. Since the biological compounds are non-symmetric, all belong to C1, so it is expected that hyper Raman and IR should give you the same result. But you see, his aim was that let's see, because it's a new spectroscopy, hyper Raman is a new spectroscopy, not many people are doing, because it needs some different background, and you just because you get a peak, that's not enough. You need to have a theoretical background also. So these people have a suitable theoretical background, suitable instrumentation, and then determination to do something new. So he progressed. Even the normal feeling says that you don't go ahead, because it's supposed to be the same spectroscopy. So, and then you see that he has found really some interesting result. And this result can be very useful, because glucose, everybody, whole world talks about glucose. You have a sugar, high sugar, low sugar, normal sugar. So if it is that somehow his experiment in which he gets quite a strong peak, in that case, obviously his technique will be quite useful. So we also had a feelings that let's see whether Raman spectroscopy can give us something new about this milk, and particularly this Banaras milk, which is not yet studied by the Raman spectroscopy. And we are happy that we got some good information, and those things are also published, and published in this year only. It's published last year, but it came out in this year, 2025. And our title was that good fat and bad fat, milk has, milk has fat, and then it is trans fatty acid is known as bad fat. Cis fatty acid is known as not bad. Is in other way it is. So we studied that one, and not only that one, we got some more information, and those information is kind of serendipity. You should work, and sometime you see that some new information comes out which actually you never thought of. So here also we saw that kind of information that I will be discussing. So this work will be discussed at the first. Okay, so these are the informations. You know the fatty acid, and it has a saturated one, 60%, monosaturated one, 30%, and polysaturated around 4%. So monosaturated fatty acid, in which we see trans fatty acid and cis fatty acid. So we say trans, cis FA, cis fatty acid, and trans FA, trans fatty acid. So trans fatty acid has a negative impact on our health. So we want to measure the trans fatty acid. We want to compare the cis and trans existence in a milk, in different varieties of milk. So this is the cis fatty acid. So it's cis because this is a monosaturated. So on this double bond, both are in one side. So this is cis, this is the acid component, and the trans is with this, there is a different one. So we have studied more than 50 milk sample, and this is the one which is average of all the things. So you see there, this all gray one, these are also existing here on the spectrum, but we have taken an average one of this, and then we see that this, according to our findings, that this is the best Raman spectra for milk as of now reported. So in which we see many peaks from 4000 to 500 wave number. So you have way stretching, symmetric scissoring of CH double bond, and then CH stretching, and many more are there which are expected, and this assignment was done based on the literature. In literature you have lots of Raman spectra for different, particularly said from developed country like Denmark, Japan. So there is no Raman spectroscopic studies for the Benares milk, and with that literature we have assigned those bands, and it's matching quite well. And these assignments are given here. So these assignments are given, and all assignments are correct. There is no ambiguity in the assignments. Then what we did, we wanted to study the fat and protein, these amide 1, amide 2 peaks. So in protein we separated the whey protein and casein protein using the normal technique. It is available in the literature. And also we separate the milk fat using the normal technique. So that we want to study this component separately, as he has done in this last, this is a normal practice. You study the component separately and then add it up and see whether your spectrum is the sum up of this individual component. So this is the raw milk spectrum. This is cow milk, raw cow milk spectrum, and this is the individual component, whey protein, casein protein, and fat. If you add up, then you get close to that, because there are many more components. As he has said that there may be many more components because of, say, Raman cross section, because of this percentage of existence. Whether their peaks will come or not, that depends. But overall, these three, if you add up, you should get this spectrum, this raw cow milk spectrum. And these bands are also assigned, and it is found to be correct. So this is in a bigger picture. So here some specific band has been discussed. So 1438 for the CH2 scissoring, 1438 for this peak, and then 1747 for the carbonyl C double bond O, 1747, these things. So 1652 band is crucial for us. Is crucial as it represents the 1652, this band, there is a mixture of more than one bands. So we are concentrating on this because here we have the amide 1 peaks hidden, we have the cis trans peaks hidden here. So we will be analyzing this band. And this is the analysis part. So we have taken the 1600 to 1700, a narrow region. And that's why if you stretch the band, it looks like stretched. This is a stretched one. If you see this part from in a spectrum where 4000 to 400 is given, then it will appear like a sharp peak. Okay, so since we have stretched the region, so it looks like a, and now you see when you want to analyze this one, then if you see the band, then clearly this is not a single band. This, say for pink one, the pink one, you see there, this is the one, you can think one band, and there is another one here, there is a hump here, and another, at least two bands are seen. So to see whether how many bands are there and what is their contribution, what is their full width at half maximum, you can use any commercially available software, like he uses Igor, we use Origin, and you can separate these two peaks mathematically. This is one peak, this is another peak. So two peaks, which is this process is called deconvolution, and it is easy with the recent software. So you can deconvolute, like for this one, you see there is a clear three peaks. This is one peak area, this is another peak area, and this is another peak. Those who are not used to this deconvolution, so for them, whenever you deconvolute, you may think n number of peaks, but if you go to the higher number of peaks, think of higher number of peaks, that will always give a good fitting. But you have to start with the minimum number of peaks. So here, say here, if you see that we are expecting a peak here, 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 here. So how many will be the peaks, number of peaks? 1, 2, 3, 4, 5, 6. So 6 should be the minimum number of, will be the number you have to tell the program to fit these peaks, bigger peak, with a 6 number of deconvoluted peak. Now if you put, instead of 6, if you put 10, obviously fitting will be better, because more number of components will be added up and fit will be better. So that you should not do, you should use the minimum number. Another thing is that how to know whether fit is good or not. Here it is not shown, but you have to always show what is the final fitted or mathematical curve that you get out of adding all these things, deconvoluted peaks. So you have used a program which says that this is experimental one, and this is the mathematically deconvoluted one. 1 peak, 2 peak, 3 peak, 4 peak, and 5 peak. Now program is telling this is the intensity of one peak, it is the intensity of the second peak. But how do you know that whether this really giving the correct measurement? So the program also give what will be the fit area combining all these things. So that usually given as a dotted line, and at the end of the fitting, if your experimental curve is like this, if your experimental curve is like this and you deconvolute it like this, and then your fit addition of this one and addition of this one together should overlap. With the experimental one. Then only you can think that fitting is proper, otherwise not. And when you are expecting a overlap together, then often you see that at some places maybe your so this is the one you get out of the fit. So obviously there is a hump here, there is a peak corresponds to this, there is a peak corresponds to this. But because of this hump, maybe you have taken more number of expected peak than the which is necessary. So the final fitting is very important. What is the final fitting? Probably you see here it is given. In this one it is given. In these are the deconvoluted area, and this red one probably the final fit curve of these deconvoluted areas, and this noisy one is the experimental data. So this is the fitting process. So through this fitting process we come to know that few important conclusion, that 1670 peak, the two things we have to note, 1650, so 1650 this one, and 1670 and 1670, say this one or this one, sorry, it should not this one. So we are talking about the fatty acid, trans and cis fatty acid. So look at this one. This 1652 is written. So this one and this one. So we now deconvolute this experimental curve into two, 1652 and 1671. It is close to the 1670 written and 1650 is written. So these two peaks are the marker band for the cis and trans. So this one is for the cis and this one is for the trans. So that's why you have written that 1670 peaks is a marker for the trans conformation. This one is for the trans, and 1650 is for the cis. So now we have a Raman marker band for this very informative information, that if we measure the 1652, then we will be knowing the quantitative, or kind of, if you measure 1650 and 1670, then we can know the ratio of these two species in your milk. So it is a kind of estimation of the cis fatty acid and trans fatty acid in your milk. And next we will be discussing what we have found in various milk. As I have said that we have studied around 50 milk, and say this is the cow milk, this is the goat milk, and these are the some commercially available milk. And we have estimated the cis and trans fatty acid. And the results are this. Results are there. That cis fatty acid is around 90 to 90%. That's good. But trans fatty acid in many commercially available milk, trans fatty acid is low, but it is seen that it can go even up to 8%, which is more than what we expect. So this analysis helps us to talk about whether the milk, commercially available milk, is good or bad, or we can also talk about the comparative, whether this company is better than this, considering the presence of cis and trans fatty acid. So we have done some more band analysis of this band, the cis trans band. These are all. This is the how the FWHM is changing, and how is the area is changing. So next, what happens is that we wanted to measure the temperature dependent Raman spectrum, temperature and time dependent Raman spectrum of milk, because we know that we usually heat the milk, we usually store the milk. What happens when you store the milk? What happens when you store the milk after heating? There are some studies where they say that milk if you boil and then consume, that actually has improved microbiological quality. There is a study by Daniel shows that boiling improves the milk's microbiological quality. In any way, we usually always boil it and then take. We also found that if you boil that cow milk, this one is that what is the relative ratio of cis trans with passage of time. So this, if you boil the cow milk and keep, then this is the trans fatty acid. This one is the trans fatty acid. This is area, means this much percentage is increasing in the milk. So trans fatty acid increase is this. And if you don't boil and keep, then this is the increase. So the boiling is better. If you don't boil, the increase of trans fatty acid is significant. And what about the cis fatty acid? This is the cis fatty acid. So this is not, there is not much significant change. And boiled, if you boil and keep, you see it is much better. It is almost steady. But if you don't boil and keep, cis fatty acid, there is a decrease. Okay. So there is a decrease for the cis fatty acid, there is an increase for the, obviously it is cis will decrease, trans has to increase. So this one again is the time dependent Raman spectrum raw cow milk, and with time. Now the conclusion, we have two conclusions for these studies. One is that we have determined the cis and trans fatty acid in the milk using the Raman spectroscopy for the Benares milk first time. And the second one is that we have shown that Raman spectroscopic studies says that boiling the milk and consuming is better than consuming milk without boiling. And it also, time dependent studies also tell that how many hours is safe and at which time this usually happens. This usually happens after 6 hours. Now this is not a biological sample, this is another story. This story is mainly to tell that how Raman spectroscopy can give you some information of a system which otherwise not possible to get using any other spectroscopy. So that kind of small story is there. It's not small story, it's a big story, but I will present in a small story. This is all about the ionic liquid. Ionic liquid, as you know, is a substance which is composed of ions, but its melting point is significantly low. So, like sodium chloride is an ionic salt. These are also ionic salt, but their melting point is less than 100 degrees centigrade. 100 is an arbitrary number fixed by the scientist who first discussed this one. So, if a salt has melting point less than 100 degrees centigrade, then we say it is ionic liquid. And if the salt is liquid at room temperature, then we say room temperature ionic liquid. What is the beauty of this one? Because this is a new kind of medium. Normally, if you see any liquid like hexane, say ether or benzene, anything, any liquid you see, all are composed of molecules, not ions. They are composed of molecules. Whenever you think of system having purely ion, then immediately you think it is a salt, like sodium chloride, potassium chloride, or a whole lot of salt that you see in the chemistry laboratory. All are salt, and salt means they are solid. But in this case, you can have a liquid which is composed of ions. So that means it significantly deviates from the conventional medium. Conventional medium is molecular and it is ionic. So that's why this is a new kind of substance, so new kind of material. So that has to be understood. And this material, the beauty of this material is that you have positive and negative one, and if you change this positive or negative, there is significant change in the property. Like you have a positive cation, this is positive, this is cation, and this is anion. So you made a combination of this cation with this anion, and then you get a low melting salt which is known as ionic liquid because its melting point is minus 81. Minus 81 means it's a liquid at room temperature. And density is this, viscosity is this, quite viscous, and this ionic conductivity is this. Electrochemical window is 6.1, means you have a window where there is no reduction or oxidation is happening of this species. Now when you change this BF4 by PF6, then you see the change in the properties. There is a significant change in the properties. Melting point from minus 81, it becomes 10. Still it is liquid at room temperature. Everything changed. Even electrochemical window is also changed. So this means that if you change this cation or anion, you can have a completely different material. So you have a lot of opportunity to make new and new material by just making different combination of cation and anion. That is why this is known as designer's solvent. Earlier people used to think this will be used as a solvent in organic chemistry, but nowadays people consider it is a new material. So we have studied this material. This material has many more good properties, like it has, the best one is that it has a negligible vapor pressure. So if you keep this ionic liquid on the desk for years, you will see the volume did not decrease because it has a negligible vapor pressure. So it has many more properties, and its application is almost everywhere. This application is everywhere. There are now the generation of ionic liquid, like initially we used to use this kind of cation and anion combination. Now new generation ionic liquids are also coming. Those are specifically usually used for some purpose. So in the new functionalized ionic liquid, this is generation 2 ionic liquid, this is generation 3 ionic liquid, and this is a unique tunable biological properties, this one. But our aim is to simply, the story is about the structural elucidation of this ionic liquid. We will be discussing very simple 2 ionic liquids. Long back we have done this one. This is one bimine cation based ionic liquid. This is just here we have added a functional group, nitrile functional group. So we have bimine means butyl imidazolium, and here it is chloride or bromide or iodide, and this is N-bimine means nitrile bimine. So this first we will be studying this one, and then whatever conclusion we are doing, we are taking the conclusion from these studies, that we will be implementing in on this molecule and to see whether our conclusion is general or not. So the story is like this. Last class I have told you that once it happened that we were crystallizing this chloride and we found that 2 different kind of crystal, and these 2 different kind of crystal later on we come to know this is a polymorph, and for that this Raman spectroscopy only helped us, because these materials are very hygroscopic. You cannot take it out and put it in the any other studies you cannot do. So this one was done in a sealed cuvette, and then we have slowly elucidated that these 2 are just polymorph of another one, and this polymorphism because of the cis-trans this configuration, whether it is a trans, whether it is a gauche, or whether it is a cis. So we found that trans and gauche conformation around this bond is responsible for the change in the Raman spectrum. And say we were lucky to have a low temperature X-ray crystallographic data. That's why we know the crystal structure, we know the molecular structure of this one, but we did not get any crystal structure of this molecule, but we got a crystal structure of this molecule, and then we see that Raman spectrum of this molecule and this molecule is very identical. Since the difference is that this molecule has chloride as an anion and this molecule has bromide as an anion, none of this anion is Raman active because it's just an atom. So definitely their structure, cation structure should be same. So this one we found this is a trans, and this is we found this is a gauche trans. So with this help of X-ray crystallography, we got this one trans of the crystal 1, and this one is the bimine bromide. So this is gauche trans, and then we concluded that this structure is this and this structure is this. So this one in fact was the first observation which says that ionic liquid can have polymorphism. So what is the importance of this polymorphism? Polymorphism means that you can in this is the ionic liquid, in the liquid you can have multiple conformation. And if there is a multiple conformation, then it is obviously that it will be difficult for them to crystallize or solidify. So then we propose that this might be one of the reasons that why such molecule has a low melting point, because they cannot crystallize or solidify because multiple conformation molecule is there in the system. So this is possible only when you have a Raman for this. Because liquid solid state structural analysis is easy, you have many, you have like single crystal X-ray crystallography, but pure liquid you do not have. If you want to do NMR, you have to add this one in a solvent, that means you are diluting it, so structure can be changed. Now, to establish this hypothesis, so what we have done, we have taken various kinds of ionic liquid, and then we found that marker band means if a particular band is appearing in your spectrum, by seeing the appearance of the band, you can tell this molecule is trans conformation or Gauss conformation. This marker band, whatever marker band we have identified, this is found to be applicable in another set of molecule, N-bemin. So we started with the bemin, and we have proved our theory for the another set of compound. This is a normal thing in science. You can have a very attractive result for one system, but if you want to say something generalized, then you have to prove that this is applicable for the another one. So these are the crystallographic data. I am not showing here. Okay, so now we have studied this one, and this is also known as functional ionic liquid, and we have done this X-ray crystallographic study, and whatever we have concluded from Raman data, we found that X-ray data is also confirming that one. So if we say that this molecule stay in a trans-trans conformation, that means through the Raman spectroscopic studies, that is correct, but because we have somehow crystallized this one and then did the X-ray crystallographic studies. X-ray crystallographic studies says yes, it is in trans-trans. So the Raman spectroscopic conclusion is correct. This one is temperature dependent studies. There is some unique conclusion from this one. So this, what we have done, we have started with a crystal. We have started with a crystal which has a Gauss band, so Gauss trans crystal, and then we started increasing the temperature. So what happens? So you have a Gauss trans crystal, pure crystal, whose conformation is Gauss trans, and then we started increasing, and once it is melted, is liquid, then we found that arising of trans-trans marker band. So this Gauss is changing to the trans. So this also says that in your liquid mixture, in your liquid, even if you are starting with a pure, conformationally pure ionic liquid, Gauss trans, but you melt it without exposing air or anything, you just melt it, and then you see you have multiple conformation. This is given by the Raman studies because you have identified the trans marker band, Gauss marker band, initially only trans marker band. When you heat it and melt, you see the arrival of Gauss marker band. So big conclusion can be drawn from this experiment. So this is one discrete observation. Once it happens that this molecule was, this crystal, this is the crystal, N-bemin iodide. So while synthesizing this one, this crystal is this transparent crystal. These are the transparent crystal. These are the. And this crystal we have a data. We have a data, and that data says it is a Gauss trans conformation of the butyl group. And when initially we don't know that whether it will be moisture sensitive or not. So when you open this, so this is RB, this is a pure RB. So when you opened it to separate this one, then all of a sudden some crystals become this opaque. This kind of opaque, big opaque crystals. But ideally it was a transparent one. And this is the opaque crystal. So we don't know why it happened. This is the first observation. Nobody has reported. So for that, you see, it is easy to find out. Just go for the Raman spectroscopy. If you are experienced, then you know that what is the Raman band, Raman spectra of this ionic liquid, because already I have shown you this N-bemin iodide Raman spectrum, and what will be the Raman spectrum of this one. You don't have to process anything. You just put it between the slides, and then you take the Raman spectrum, and then you find that very interesting observation is that you find a band at 3300. So that means it absorbed the water. Okay. So just by Raman spectroscopy you can tell that it has absorbed the water. And then not only just absorb the water, then next slide onwards I will show that it changes also, structure is also changes. So structure changes. So this is a kind of serendipity, because we do not expect that we will have a crystal structure of the molecule, pure molecule. We will have a crystal structure when it absorbs the water. But in this case, it was a good luck that I have observed, I have obtained a crystal in which there is a water molecule. This is a water molecule. So this is a cation-anion combination whose X-ray structure I have, and this, when water molecule is included, in that case also I have the X-ray structure. So now I have the information, what is the exact conformation from the X-ray studies, and I have the information from the Raman studies, what are the marker bands. Then it is found that because of this water molecule inclusion, there is a change in the conformation from trans-trans to trans-gauche. So this is the first example in which it is shown that simple water molecule can change the structure of your cation. So this is a big thing, because you know that when structure is changed, its property will be changed. So that's why many times this chemist people, they are worried about whether this water is absorbing or not. This is one example in which we have shown that apparently innocent water molecule changes the structure of the cation. So this one was published in good journal, Journal of Physical Chemistry. So this is the, you see how it changes the structure, this packing. This one is that. So this position is similar to that of, this is with water molecule, okay, and this is without water molecule, So without water molecule, it's like some block. We have shown it like imagine like a block, simple block-like between, say you can think of 4 blocks, and the 4 blocks is encapsulating 2 pillars of anion. So this is the same pattern for bimine chloride and N-bimine chloride. Same pattern. But when water comes in, you see the complete structure is disturbed. Simple water disturbed everything. So obviously if you are using this molecule in a reaction or in something, if that shows, obviously this will not show because structure is changed. Now, so what we started with a single crystal, pure single crystal in which water is not there. We took the Raman spectrum, and then we took the Raman spectrum of the opaque, that which happened suddenly. We took this opaque crystal, and then we intentionally exposed this single crystal to the air for some time, few seconds, and we took this Raman spectrum, and we found that Raman spectrum, this for the single crystal, this band, marker band was almost not there, and in this case it is prominent, and here also prominent. So what we have observed is because of the exposure to the moisture. So simply by studying the Raman spectroscopy, we can do this one. This is another simple story that also we have published recently from here. So this is that there is a anion like this, we say NTF2, tiflamide. So this is the anion. So this is the anion. And through Raman spectroscopic studies, we have shown for the first time that this anion also has a multiple conformation. This anion can be in cissoid, or this anion can be in transoid. In the ionic liquid, we found that there is a specific distribution of cissoid and transoid conformation for this ionic liquid. This was published in Journal of Molecular Structure. So with this, I am stopping here, and I must acknowledge this person, because in his lab only I have been exposed to Raman Spectroscopy in Tokyo University, where this Professor Hiramatsu was there. But when I joined, he just left. And this is and throughout this year, I have been pursuing Raman spectroscopy because of my students. They are the students who are doing Raman spectroscopy. I don't do myself, so they do. So I must acknowledge them for everything, even for organizing this conference, a workshop. And money is necessary, so my funding agency should be acknowledged. And the Department of Chemistry, where I'm a work employee, they are also acknowledged. But this memory is really something which difficult to forget. This is the entrance, main gate entrance of Tokyo University. And this tree is called Icho tree, and this tree leaf symbol. This tree's leaf symbol is the emblem of Tokyo University. Tokyo University is one of the oldest university in Japan, and it is one of the best in the world. Recently it ranked 10th. So it's really nice to be there. So I must acknowledge my professor, Professor Hiro Hamaguchi, for all these Raman activities. With this, so it's the end of my talk and end of our talks. Thank you. So now we have some time, maybe we have some time to take